Kubernetes sits at the center of how AI runs in production, not just the models, but the infrastructure underneath, where workloads land, how they scale, how they share GPUs, and how can they still run when real traffic hit those models. And this is exactly where most people are getting stuck now. There is plenty of content on Kubernetes and tons of content on AI. Almost nothing shows you how these two come together for real production systems. So this is what this video is all about. No matter where you are starting from, I've got you covered. If you're a beginner, make sure you are reviewing my part 1 where I've covered the updated stack for traditional Kubernetes workloads. For intermediate learners, we'll connect the dots between concepts and the real-time workloads. For seasoned pros, we are diving straight into how these systems are designed. Hi, I'm Vishakha, an AI solutions architect, and this is part 2 of my series. I've broken down this video into 6 core buckets: extending Kubernetes, the CRDs and operators work, to schedule accelerated workloads. We'll dive into distributed training, inference serving, how autoscaling works for AI workloads, and the last one, observability stack. Let's dive in. Now, you already know the baseline of how Kubernetes works. The control loop, the endless YAML, the control plane that's obsessively trying to match your reality to your declarative state. This part doesn't change a single one of those rules. The control plane is the same, scheduler is the same, the declarative model is identical, but spinning up a standard Nginx web server and deploying a 70 billion parameter model are entirely two different challenges. One needs a basic CPU and an open port. The other demands multiple GPUs, over half a terabyte of unified memory, runtime optimized with intense tensor operations, and a scheduler smart enough to co-locate those GPUs. Now, vanilla Kubernetes doesn't know any of that out of the box, but it was designed to be extended. That's exactly what the AI ecosystem has done. Every tool and workflow we cover in this part is just a new trick within the Kubernetes ecosystem. So let's dive into our first bucket, that is how Kubernetes is extended. Now remember the control plane we covered in part 1? A controller watches the cluster, sees a gap between the desired and the actual state, and closes it. Deployment controller does this for pods. Replica set controller does it for replicas. And here's the thing, you can write your own controller, and if you want your controller to manage a different kind of object, not a pod, not a deployment, but something that you invented for your specific environment, you can register that with Kubernetes using a custom resource definition, aka CRDs. Now let me walk you through with an example. Let's say I want to run a new object named vrocks, also known as Vishakha rocks. What that object does is run a monitor around what each user runs inside that cluster, basically tracking user activity. We'll start with writing a custom resource definition. So the first step here is to define the CRD. You write a YAML file that says, hey Kubernetes, there's a new kind of object in the world called vrocks. Here is its schema, target namespace to watch, an alert threshold, and a reporting interval. So start accepting it. Apply it once with the kubectl apply command, and from that moment onwards, kubectl get vrocks works. Cluster understands a new type, but this custom resource definition is just the shape. It doesn't do anything on its own. This is where you need to create a vrock object. Now, someone on your platform team creates a vrock instance declaring the desired monitoring state for a particular namespace. The object gets stored in etcd cluster, holds it, but still nothing happens because the controller isn't running yet. Now, what is controller? It is a small program typically written in Go or Python running a reconcile loop. Every time a vrock object is created, updated, or deleted, it runs your logic. It can fetch the vrock object and read its specs such as threshold, interval, target namespace. Then it lists all the pod in that namespace and read usage from the metric server. Can do a bunch of other things like emitting Prometheus metrics per user. So Grafana can visualize it, alerting the user, and a bunch of other activities. You can customize it. Now you deploy this controller itself as a deployment. So Kubernetes keeps it running. It needs a service account with RBAC permissions to list pods and read metrics. So there are a bunch of other Kubernetes objects that you can deploy with this custom logic, but hope you understand the essence of what the controller does here. Now, so far you have a CRD, you have created an object, and you're running a controller. But how can you ship it to other teams? So you package that CRD, the controller deployment, and all the RBAC rules together into a single Helm chart someone can install with one command. That bundle is called the operator. Install it and your cluster gains a new capability it didn't have before. So when you write kubectl describe vrock and you give a username, It tells you who's over that threshold right now. And that's the pattern every AI tool in this video follows. A CRD is just the shape. You need a controller watching for those objects and turning them into actual work. When you bundle a CRD plus its controller together, that bundle is called an operator. So in essence, nobody had to patch Kubernetes core objects to support distributed training, inference, and other AI related activities. They wrote an operator, and the steps were pretty straightforward. Install the operator and your cluster suddenly understands a new class of infrastructure. That's the superpower. Now let's dive into our second bucket. That's our scheduling bucket. The scheduling task has changed for accelerated workloads with GPUs. And here's the story. You spin up a GPU node, it joins your cluster, you look at kubectl get nodes, and you can see the node is ready. But when you try to schedule a pod on that GPU node, it just sits there pending forever. That's because Kubernetes has no idea that the GPU exists. Now one may ask, how does Kubernetes knows about a CPU node but cannot detect a GPU node? The reason for that is the kubelet on every node knows about CPU and memory because Linux exposes those. But GPUs are different and are not a first-class Linux resource. Something has to tell Kubernetes that there's a GPU node in the cluster. So in order to fix that, you need to first install a GPU operator. It comes as a Helm chart, and once you run the Helm install command, it drops a daemon set on every node. Now the daemon set here installs an NVIDIA device plugin, which does one job. It talks to the kubelet and says that this node has 8 GPUs. Here they are. From that moment onwards, the node advertises those 8 GPUs to the API server. The Kubernetes scheduler can now see it, count it, and place workloads on it. Here's how your pod spec looks like. It needs 3 things: a resource request, a runtime class name, and a toleration matching the GPU node taint. So the job of the taint here is to keep your CPU workloads off your expensive GPU nodes. And the toleration you add to your pod says, I know this node is tainted, I belong here anyway. Together, they act like a bouncer. The right workloads get in, everything else waits outside. Now, if you miss any of those 3 things, your pod either pens forever or crashes on a CPU node. And if you add all 3 together, the pod lands exactly where it needs to be. Now, our next bucket is training workloads. Here we are talking about what you actually deploy in those clusters with the accelerator machines. There are a bunch of different AI workloads depending on different needs, but 2 workload patterns in AI infrastructure you must know. One is training, another one is inference. They have different shapes, different life cycles, and totally different failure modes. Also, Kubernetes handles them differently. Think of training as a batch job. It has a start, it runs, it finishes. You're not serving any traffic here. There's no external user getting something out of this training job. This is when like your model is being trained. And the training task mostly looks like crunching data, computing gradients, updating model weights, and writing a model file at the end that you can deploy in production for the external users. Now, there are also different ways you can do training. For a single GPU training, the job object that we discussed in part 1 is exactly right. One pod runs to completion, done. Distributed training is where things get interesting. You have worker 0, worker 1, worker 2, each holding a shard of the model or a shard of the data. They need to find each other, coordinate, synchronize gradients, and recover gracefully if one crashes. Now, if you don't know about gradient, it's just a mathematical compass that measures the slope or rate of change of your model's errors, and that is used to point the model to the right direction. Now, coming back to Kubernetes, a plain job doesn't know how to do any of that, and hence different training operators got created. Now, this is where the training operators become very useful. For example, there's a PyTorch training operator. You describe a PyTorch job, how many workers, how many GPUs each, what image, and the operator handles the rest. It creates the pods, injects the right environment variables so the PyTorch distributed backend can discover peers, sets up the master process, and restarts failed workers without killing the whole job. So you see, the PyTorch operator was designed to do a bunch of things here. You don't have to manually create jobs now, it will create on behalf of you. You just have to create a manifest with a kind PyTorch job and it will do the magic. Now, there are other open source tools as well that you should be familiar with. One is MLflow. This is used for experiment tracking plus model registry. Your training job runs inside a pod MLflow runs alongside it as a service in the cluster. As your training loop executes, it logs metrics, parameters, and artifacts to MLflow. And when the run finishes, the trained model gets registered in the MLflow model registry with a version. A stage could be staging or production, and a URI pointing to the weights on storage. Every downstream system, such as your CI pipeline, your team, knows exactly which model version is in production and where it lives. So think of it as a paper trail between training and serving. Now, another tool that you must know is Kubeflow. It's an end-to-end ML workflow orchestrator. A training run is never just one step. You pre-process data, run training, evaluate the model, compare it against the current production model, register if it's better, and then trigger a rollout to the production servers. Kubeflow pipelines lets you define that entire sequence as a DAG. A DAG stands for Directed Acyclic Graph. In the context of Kubernetes and data pipelines, it's used to define, schedule, and execute complex workflows. Now, since it's Kubeflow, each step that happens is a containerized task running as a Kubernetes pod. The pipeline controller manages dependencies, retries failures, passes artifacts between steps, and gives you a UI to track every run. It's basically the glue between your data prep, training job, evaluation logic, and deployment trigger. You basically write the steps, and Kubeflow handles the orchestration. Now, as we know, Kubernetes is great at orchestrating containers, but distributed training needs something more specialized. It needs some mechanism for parallel task execution, distributed Python processing, GPU-aware scheduling again, multi-node training coordination, and scalable inference execution. This is where Ray comes in. That Ray acts as a distributed compute layer that helps AI workloads scale efficiently across Kubernetes clusters. It runs on Kubernetes via the Kuberay operator, which registers a Ray cluster CRD. It describes a head node and worker nodes. Here, the Kuberay operator creates and manages the pods, and RayServe sits on top for dynamic model serving with Python native routing. So if your workload is Python heavy, data heavy, and doesn't fit neatly into a training job or an inference service, Ray is another tool that can fill the gap. Now, just don't stop yourself here. After watching the whole video, go and dive into these tools and see why one will be used for your ecosystem, and just learn about it a little more. Even if you're not really deploying it, knowing about these tools can definitely help. Now, my favorite bucket. This is the inference serving and the deployment bucket. Inference is the opposite shape of training. It's not a job that finishes. It's a long-running service. A pod that loads your model into GPU memory, opens a port, and stays alive, waiting for requests. When you deploy a model for inference on Kubernetes, three layers come together. The first is the model itself. It comes from somewhere like Hugging Face, an S3 bucket, a model registry. Then an init container pulls it down before your serving pod ever starts. It lands on a persistent volume claim. That's the shared storage that survives pod restarts. And the model weights don't live inside your container image. They live on the volume. Your image is just the engine. The second layer is a serving engine. This is the runtime that loads those weights into GPU memory and handles everything that happened after. Tokenization, patching, KV cache management, streaming tokens back. In enterprise clusters, you might have heard about these engines like vLLM, SGLang, CRDLLM. They all have different optimization strategies, and each one runs as a container, exposes an OpenAI compatible endpoint, and gets wrapped by the same Kubernetes objects. Third layer belongs to the Kubernetes objects. A deployment keeps your serving pods running and handles rollouts, and a service gives it a stable internal endpoint. Now here's where KServe also comes in. It provides a Kubernetes native model serving layer, which helps simplifying deployment, scaling, and managing LLM inference workloads in production. Again, KServe is bundled as an operator, and when you install it, it deploys controllers to watch custom resources like inference service, serving runtime, cluster serving runtime. These operator controllers automatically manages a bunch of things. In addition, it helps you apply deployment strategies for different model versions. For example, KServe's inference serving CRD can add canary routing, where you can just route 5% of traffic to a new model version, watch the metrics, and ramp up only when it looks Good. Now here's a simple request journey. The request comes in through the service, it hits the engine reads from GPU memory, the token streams back out. That's the full path. Last piece. You have your inference service running. Now how do you scale it when there's a lot of traffic? That's our next bucket. Autoscaling for AI. Remember the HPA from part 1? It watches CPU utilization, memory, etc. If it climbs a certain threshold, it adds more replicas. If it drops, the HPA just removes the pods. Now here's the problem. An LLM running at full capacity hardly moves the CPU needle. I mean, it does move, but it's not the main metric that's running the LLMs. And in the meantime, your GPU is saturated, there are 100 requests queued, and tokens are only generated as fast as the hardware allows. And CPU is still at 15%. In this case, HPC is nothing. It doesn't scale and your users wait. In this case, you need to watch custom metrics that are required for LLM workloads. How many requests are sitting there right now? What is the engine queue length? And when those numbers climb, you need more pods. When it drains, you can scale them back down. These custom metrics can be scraped through Prometheus, but HPA can't read it. KEDA can. KEDA stands for Kubernetes Event-Driven Autoscaling. It is another operator. You install it once and it registered a scaled object CRD. You point that scaled object at your model deployment, tell it to watch that Prometheus query, set a threshold of 5 waiting requests per replica, and that's it. When the queue drains, pods scale down. Same control loop, smarter metrics. Couple of things you have to be mindful here is KEDA can scale to 0. So you can set the minimum replica count to 0 here when there's no traffic. Also, you have to be aware of cold starts because these are big models and it takes time to load it into the GPU memory. You can add some internal optimizations for it. Now, a last bucket, observability. You can't operate what you can't see. And AI workloads can break in ways that CPU dashboards won't catch. The stack here is standard Kubernetes. Prometheus scrapes metrics, Grafana visualizes them. What changes is what you scrape and how you instrument the workloads. Now, basic observability setup looks like this. You install Prometheus operator using Helm. This operator deploys and manages the Prometheus service, alert manager, and monitoring CRDs like service monitor and pod monitor. Here there are two components. Cube state metrics exposes Kubernetes object and state metrics, while node exporter exposes node level CPU, memory disk, and network metrics. Grafana gets deployed separately via Helm or Grafana operator and it connects to Prometheus as a data source. Dashboards then visualizes Kubernetes, GPU, Ray, KServe, or any AI inference metrics scraped by Prometheus. Now there are a bunch of layers for AI workloads. On the hardware layer, GPU health comes from the NVIDIA DCGM exporter. It ships with a GPU operator and it exposes GPU utilization, memory use, temperature, power draw, and errors per device. If the utilization is low while your queue is full, something's wrong with the workload, not the hardware. The next layer is where the serving engine comes in. There are custom metrics emitted by different backend engines, like vLLM exposes their own set of metrics, different for SGLang and different for TRT-LLM, and they all expose Prometheus endpoints. There are a bunch of signals that matter, such as request waiting in the queue, time to first token, tokens per second, KV cache utilization, etc. These are the numbers that tell you if the users are getting faster responses. There are also training metrics layer, which comes from MLflow for the experiment side and from PyTorch operator from the infrastructure side. Now that's a wrap. Now one thing that doesn't change with Kubernetes, you have the same cluster, same control loop, same declarative model. What changed here is the layer of objects on top. Operators that taught Kubernetes about GPUs, training jobs, inference workloads, auto-scaling, and observability. That's modern AI infrastructure on Kubernetes. Now, again, I would ask you to not stop here. Go dive into these tools, understand what they do and how they do it. Create a learning roadmap for yourself. Hope this helps and see you in the next video.